Let's talk. Whew. Let my heart rate come down a little bit. All right. First things first, let's go ahead and quickly I just want to see what y'all are thinking. What type of function would you think an A would be?
Exponential.
Exponential. So what evidence did we have that this is exponential? Right, so it's exponential. So you say multiplying by 2. So it has a multiplicative rate of change times 2. We all good with that idea? What about 8b?
We got quadratic.
Quadratic, exponential. We got a little bit of differing opinion here. What about C first? Let's look at C.
Linear.
Linear, why is it linear?
Additive rate of change by 2.
Alright, there we go. So plus 2 every time. So that's an additive rate of change plus 2. Okay. So B is the one we have a little bit of debate about.
I don't even know, I'm guessing.
So if you say exponential, what does that mean? So we're repeatedly multiplying by the same thing every time, right? It's multiplicative rate of change. Anyone have an idea what we could multiply by here?
Nothing.
Nothing, right? I don't see anything to multiply by. Okay, so you said quadratic though, right, Trey? So if it's quadratic, what does that mean?
You got linear rate of change.
Linear rate of change. So that's similar to linear in the sense that we need to look at sets of differences. What's the difference from 36 to 49?
13.
13. When you say 13, are we
Add plus 13.
Plus 15.
Plus 15.
Plus 18.
Maybe that's plus 17. And then plus 19.
That's important because what's my additive rate of change?
2.
For that at least. Notice, and this is important, the second set of differences, right? The second differences, that's constant, or a constant additive. If this set of differences is constant additive, that means this rate of change is what? Right, so the first difference is, that defines our rate of change. What is that first set of differences?
Additive.
This is a constant additive rate of change. Like this is additive. Remember, this is constant additive. What type of function has a constant additive rate of change? Say it again. Linear. So if this is constant additive, in black we have, that's a linear rate of change. And if the first set of differences is a linear rate of change, f of x is quadratic. So we have to look at those sets of differences or those ratios in order to determine all that information. We good there? Any questions? You good, Dwan? Tony, you good? Brooklyn, you good? Cool. Everybody good? Alright, so go ahead and put 6.1 away for just a second. We're going to wrap up Gold Rush.
Y'all turned that in.
Why?
And that was the homework.
Nope.
What was the homework?
The homework was the sheet that said March 22nd homework, March 23rd homework, March 24th homework.
That's it. Okay.
Dawn, you didn't turn in Gold Rush. You turned in the homework.
Oh. So what is Gold Rush then?
It's the one with Gold Rush on there, and it had the people looking for gold. Yeah, that one.
I thought they both came together.
Task 1, Gold Rush task. Maximizing area. Yes, ma'am.
I left my homework at home. Could I turn it online after school today?
Yes. You can send me a message on Schoology, or I might open something up for you to turn in.
Okay.
Okay. Really quickly as a recap, we already talked about it. A quadratic function both increases and decreases, and it has what type of rate of change?
Linear.
Linear rate of change, right? And so remember how we were looking, we first looked here when it was going by 5s, but then we also said, well, what about if it was going by 1s? Would it still be that linear rate of change? And so we looked here, and it was plus 47, plus 45, plus 43, plus 41, so on and so forth, right? So when we look at this, don't forget, the first differences, that's my rate of change. The first differences is the rate of change. Is that rate of change going by the same thing every time? Like, are we adding 3 all the way through here?
No.
No. It's changing how much we're adding by, right? So the first difference is my rate of change is changing.
So let's do the minus 2.
But notice how the second difference is that is constant, right? So if the second difference is constant, we just talked about it, that means the first differences, right, that's the rate of change, is linear. And so that's why the area function is what type of function?
Quadratic.
Quadratic, right? A quadratic function has what type of rate of change? Linear. So Destiny, if you have something with a linear rate of change, it's going to be what type of function? What's your name, Destiny?
Oh, geez, no.
So what is it going to be?
Quadratic.
Quadratic, right? We need to notice that relationship. If it's quadratic, it has a linear rate of change. So if it has a linear rate of change, it's going to be quadratic function. Now, this is important to notice because this is a detail that has been tripping students up all day today. You have to separate a linear function from a linear rate of change. A linear function has a constant additive rate of change. A linear rate of change, though, comes from a quadratic function. Okay, so note the difference between function and rate of change. Which technically, and this is what's a little weird, this first set of differences is a linear function, but it's also the rate of change for this function, so it's also a linear rate of change. That is it for the end of tabular representations. What other mathematical, and so that's what's unique about a quadratic function is a tabular representation. But what are the other mathematical representations we still need to look at?
Graph.
We still got to look at graphical. What else?
Verbal.
So remember, this problem actually started as a verbal, right? It started as a word problem that we had to figure out. And we drew rectangles, we made pictures to help us figure it out. Then we made tables, made graphs, but what else? What is the fifth mathematical representation? Kind of the focus of this course.
Algebraic.
Say it louder.
Algebraic.
Algebraic. What do we mean by algebraic? Expressions, equations, and inequalities, right? Now in this case we're just going to be looking at equations. But yeah, if we're saying algebraic, we mean equations, inequalities, expressions. And when we talk about equations, by the way, this is where you need to start writing. Right? So quadratic, algebraic representations. So if we are talking about a quadratic algebraic representation, we can talk about a recursive or what other type of model?
Explicit.
Explicit, that's what you're trying to go for, right? So we have recursive models and we have explicit models. Okay? We are going to start with a recursive model. Now, before we get too far into this, please understand me very clearly. The focus for me when it comes to algebraic representations in this unit is that you can tell a quadratic equation versus linear or exponential. you will practice writing quadratic equations. But I will not be heavily testing that on this unit. Next unit will be all about quadratic equations. The focus of this unit is you need to be able to tell the difference between a quadratic equation and a linear or exponential equation. Does that make sense? So focus on what makes quadratic quadratic. Trey, how do we always start recursive equations?
How do you call it, a function thing? Like the E?
Function notation can be f of n equals, hey guys,
What show is up there?
show enough. Anybody see anything about recursive models?
F of N equals F parentheses N minus 1.
Okay. Now, I want you to notice how over there it then has this little star and then the rate of change, right? The reason why it has that star is that's not a mathematical symbol. That's not saying multiplication. It is saying that we are doing some operation to apply the rate of change. Now, if it is linear, we are constantly adding by something, adding the same amount every single time to the previous term, right? If it's exponential, we're constantly multiplying by the same thing every time. Are we constantly doing the same thing every time?
No.
No. But remember what y'all said earlier, this first set of differences is what type of function?
Linear.
It's linear, right? Hey, can I write the equation of a line? Is that possible? So if I can write the equation of this line, I can apply it as this rate of change. Right? So for a quadratic function, write the linear equation of the rate of change. Right? If we're trying to write a recursive equation for a quadratic, well, we need to figure out what the equation of this rate of change is. Now, one thing I do want to point out is, do you think I have to use this table that goes by ones, or could I use this table that's going by fives? I could go by fives? Okay, so let me point this out. This is relating f of n, the current output, to f of n minus 1, which is how many before the current. It's what?
The ones.
It's got to go by ones. I'm only going one before right here, right? So we need to notice when I say f of n and f of n minus 1, I'm only going by ones, so I have to use the table that goes by ones. Make sense? There is a way to do it by fives, but we're going to focus on the going by ones, okay? So I need to write an equation for this line right there. Well, RJ, give me one equation of a line. Just tell me the name or the equation. RJ, come on, look at me. You tell me you don't know any of the three equations of a line. Keep thinking about it. I'm going to come back to you next. Tony, give me one equation of a line. Guys, are you for real?
I'm so confused.
You have no clue what you can do for the equation of a line. Go on.
You know, ask me.
Y'all are gonna feel so silly in a second when someone finally gives me an equation in a line. You're like, dang, I'm being big dumb. Not big brain, big dumb for a second. Trey. You gotta be kidding me.
Oh my god.
Dude.
What's the rate of change of a line called?
Boundary line?
You can have a boundary line.
No, slope intercept.
Slope intercept! Oh my gosh!
Oh, you talking about them?
Yeah, you mean dim the equations of a line?
Point slope.
Point slope! Oh!
Standard.
And standard! Come on now! Y'all acting like I ain't never taught you anything.
Yeah, all of that.
Y'all embarrassing me. I'm recording this and everything, and then people will be watching like, man, that guy don't teach anything to those kids.
Called it 4K.
Alright? Y equals mx plus b. That's my slope intercept. Y equals m times x minus x1 plus y1. That's my point slope. Man, y'all hurting my heart. Jeez. I thought I got my heart rate going earlier when I was walking back up here. Oh no, my students don't know anything.
We know it, we just forgot.
Yeah, no, you didn't forget it. You didn't want to think. Alright.
Couldn't even.
These are the three equations of a line that we have studied so far. Remember, we're trying to write the equation of a line. Can we use standard for this problem?
Yeah. Wait.
Do you know what A, B, and C are?
No. We can use slope intercept. Yeah.
Okay. So to use slope intercept, we have to have a slope and what else?
Intercept.
Y-intercept.
Thank you, a y-intercept. Do you know what the slope is?
Yeah, I need the rate of change.
It is, well, yes, it's which rate of change?
2.
It's not 2 up there.
-2.
It's -2, right? Remember, it's the constant additive rate of change, right? Which is -2. See how that's the rate of change for this rate of change?
Didn't change.
Okay, so it's -2. So we do have m equals -2. So what's the y-intercept?
You want to be 600.
Y equals -6x.
Hey, I need y'all to listen to this. What is a y-intercept?
The point is on the y.
It's when points on the y-axis, what?
When x equals 0.
Which is when x is equal to 0. Look at this table. Do you have an x value of 0 up there?
Yep.
Bro.
Wait, no.
Up here, when we're going by ones?
Yeah.
No.
Is that y-intercept up there? Nope.
That's
So can I use slope intercept?
no.
So what do I have to use?
Point slope.
Point slope. Notice I have a slope of -2. That's this -2 right here. I still need a point though, which we can choose any point we want. What point do you want to use?
You use any point?
Huh?
Any point?
Any point.
3.
3? This 3? Okay. So the point's going to be 3 comma what?
0. Wait, no.
There's a 47 here. There's a 1, what is that, 51? No, 41. Here. And there's those other numbers on the right. What's the y value going to be for that point?
47.
47? Why 47? You talking about this one?
Yes, sir.
But what are you trying to write an equation of? You're trying to write the equation of a line for what? Guys, we're trying to do a recursive equation.
Quadratic.
We still need the what for the recursive equation?
Rate of change.
Rate of change. So we're trying to write an equation not for the base, not for the area, but for the rate of change. Right? Is this 47 a part of that rate of change? No. I have the x value 3. What is the y value for the rate of change?
Would it be 141?
Is that the rate of change?
Oh no, it'll be 45.
at 45. You've got to remember what we're trying to do. It helps to pick up a pencil and write these notes down. Right? That is the y value of the rate of change. You are writing an equation for the rate of change. The equation for the rate of change. So, we're using point slope. What is that?
About -2.
Thank you!
Alright.
We literally have m equals -2, right? You said it was slope, right? Here's my slope for the linear rate of change. Parentheses, x minus 3, x1 plus
Yeah.
the 45. You see how this is the equation for the rate of change?
Then you said distribute.
Don't even need to do that. Remember how it was star rate of change, right?
So you gonna solve it?
So minus 2 times x minus 3 plus 45. And no, you would not solve. You could simplify. Talking about when you were distributing and stuff, that would be simplifying, not solving. Remember, when you solve, you're finding what makes the equation true. You were trying to simplify, not solve. Okay. Have we ever seen a rate of change with a variable in it?
Yes.
The rate of change with a variable?
No.
No. So is that kind of unique to a quadratic?
Yes, sir.
Right? Quadratic equations. And don't forget, this is the equation of a what? And what kind of rate of change does a quadratic function have?
Point slope. Whoa.
Linear, right? So we use point slope form of a line. We need to remember quadratic equations have linear rates of change. That is a huge part to know here. Now there's one thing I'm missing from that recursive. Does anyone know what it is? So remember, this is the equation of the rate of change, right? But this is still a recursive model for the area. So this is the equation for the rate of change, but if I look at the area, a height of 1 had an area of 49. That's my starting point. Now, please hear me very clearly. Writing the equation for the recursive equation is harder. It will take us a while to practice it. I know that. I am not expecting you to know that really well. Remember what I told you from the beginning is you should be able to tell a quadratic equation versus linear exponential. So you should be able to look at something like that and say, hey, that's a recursive model, but it has a linear rate of change, so it is quadratic. That's what you need to be able to do. But don't forget, you need a rate of change and a starting point. Now, for the explicit equation, again, we're going to write explicit equations a ton next unit. Right now, I need you to be able to know how an explicit quadratic equation is different from a, what other types of functions? How a quadratic is different from a exponential or a linear, thank you. So, when we talk about this area here, right, how did we calculate that area every single time? What did we do?
When it had to be for 100 meters.
The perimeter had to be 100 meters, but how did you calculate this area? How did you use this 5 and this 45 to get 245? So you were multiplying the,
Height and base.
thank you, right? Fundamentally, we should know that the area is equal to the height times the base, or base times the height. Dewan, it helps to have a pencil in hand writing these notes down. Y'all, you don't wait to write notes down, one, until I tell you to, or two, when I'm done talking. You write notes as we're going over this. You are slowing yourself down and slowing us down. These are important skills you got to learn before you graduate high school. Legitimately, you got to learn how to take notes as people are talking. However, how many independent variables do I now have? 2. Can you type that into any calculator to graph it? CJ, have we ever done 2 different variables, h and b? You can't do 2 variables like that. You have to rewrite it in terms of 1 variable. A is my output, so I'm going to say f of x. Right? Now I want you to notice I'm changing the height, right? Like I choose what the height is. So I'm going to let my height be x. So I'm substituting x in for h. So my height is my independent variable. That's what I'm changing. Now, if I just put a b here, I still have how many independent variables? 2. Can I have 2 independent variables? Heck to the nom. So, we need to come back over here and figure out an expression for the base determined by x. So, I want you to think about this. How did you know that the base was 45 when the height was 5? Or how did you know that the base was 40 when the height was 10? Whoa, let's implement this. Raise your hand if you want to talk, just because I want to honor people who started first. Brooklyn, go ahead, and then we'll go to Tony, then Dewan. Because what had to equal 50?
40 and 10.
40 and 10, meaning the sum, right, of the base and the height had to be 50. Is that what you're going to say, Dewan? We got some more we can add on to it. Tony, you have anything else to add on to that? Okay, let me ask you this. If the height was 12 meters, how would you figure out what the base is?
Subtract 12 and 50.
Wait, so you're doing, to get the base, you're doing 50 minus 12? Okay. Could that have held true when we had 5? It was 50 minus 5?
Yeah.
Yeah? What about when the height was 10? You would have done 50 minus 10?
Yeah.
Well, what if the height was x? It would be 50 minus. Is that an expression that we could substitute in for the base?
Yep.
That makes sense so far? And again, we're going to be working on quadratics a lot. Be aware of that. This is the first time you're learning this, so should you know how to do this perfectly yet? That's why this is where I'm leading you on something that you did not know. But I need you to take notes so you can study it later. So the base is being represented by 50 minus x. Now this is where we're going to learn something important about a quadratic equation. Hey Dewan, what do you think I could do here to simplify?
Distribute.
Tony, do you agree that we could distribute here?
Mm-hmm.
Okay, what are we going to distribute? Not just x. And there's the 50 is being grouped with the minus x. We're going to distribute the, what is this?
Multiplication.
Multiplication by X, right? We're not just distributing x, we're distributing that multiplication by x. And so I'm going to show those as separate steps. X times 50 minus x times x. Hey CJ,
Okay.
what is x times 50?
Magnitude.
How would I rewrite that? 50x, right? And RJ, what would be minus x times x?
X.
Negative.
Negative.
It is negative. Is it just an x? Like how does x times x become just x?
Because it goes 1 times 1.
It's true, but what would it be if it was 2 times 2?
4.
Wait, so, because like by your logic, x times x equals x. That'd be 2 times 2 equals 2. Is that true?
No.
It'll be 2x.
X squared.
Yeah.
X squared, not 2x.
Yeah, x squared.
Remember, a positive exponent is repeated multiplication. You see how we're repeatedly multiplying? Okay. Now, traditionally, we do write our highest power first. You say how x squared is a higher power than x to the first, right? So that's which power is this?
Second.
Second, whereas this is just the first power, right? So, that's an example of a quadratic equation. Here's an example of a linear equation. And here's an example of an exponential. We need to be able to recognize each of these different types of equations. So how is a quadratic equation different from a linear versus an exponential?
Zero.
What about it?
The exponents first.
What do you mean?
X squared.
It is x squared, meaning the highest power is the, and there's an exponent here. Technically there's an exponent there. So what makes the quadratic different? But this has an exponent, it's just to the first power. This has an exponent, it's just an exponent of x. They all have exponents. Actually, there's only one variable, x. May show up 2 different times, but it's still just one variable, x. Say again?
You multiply.
Where?
3 times 2x. And
Well, that's 3 times 2 raised to the x. Guys, y'all are missing important things here. Y'all are dancing around it. You say there's an exponent here, meaning that the exponent is what?